Hi, I'm Prof. Joe. I'm a professor for automation and measurement technology at the University of Kempten, the very south of Bavaria. And this is chapter 2 of my lecture Measurement Technology, which I'm giving at that university. This lecture is AI accompanied. That means you get a link down below to a prepared GPT which contains all the facts, all the content you need to learn for this lecture or to learn this lecture. That means these videos only are meant to give you focus, to explain difficulties and to give you some context around the stuff, around the things, around the facts, around the pure facts. So, topic today is about measurement, errors, an essential part of measurement technology at all. What does that mean? What is an error doing? Why are those errors so important? It's a simple fact. A measurement value without an error, without a measurement uncertainty which is given, is worth nothing. You don't know nothing about that value just given the pure fact that, for example, it's 25 degrees. You don't know if somebody just felt that temperature or he really measured it, and that makes a real huge difference. And it has a major influence on the errors accompanied to that measurement value. So in reality, normally you have that measurement device, which is in the center of all our doings in measurement technology. Now that measurement device will measure a measurement quantity given by the measurement object over here. So it's the measurement device. And it will produce a measurement value we want to have. This measurement value explains us what this measurement quantity is about. It gives us some rough idea, in the best case, a good idea of how big that measurement quantity presumably is. So we have some problems. We have some influences from the outside, we have some influences from the inside, and we have some influences from our measurement object itself. Meaning, for example, we have some batteries in here. That's a measurement device which is attached to a certain voltage, which indeed produces some heat in the measurement device, and so on. There are influences in the measurement device itself. On the other hand, the measurement object itself also influences that measurement device. Example, you are measuring a temperature. Your temperature sensor is attached to the object and will heat up by the object. That is something you want to have. But on the other hand, the pure form, the material the object is made of, and other factors will influence how that temperature sensor will be warmed up when touching the measurement object. That is some influence of the measurement object to our measurement device. And for sure, there are influences from the outside, which are mostly temperature and humidity, which should always be taken into account, which influence our measurement device and our measurement object and the whole measurement itself. Having said that, the influences given here are all somehow human-made. Meaning, you choose the measurement device. You know how it's working. You know perhaps what influences within that measurement device are important. So for example, you know it will heat up when used for 2 hours by 2 degrees. That's a fact. You could include into your measurement description, including the measurement value. Most people don't do that, actually. On the other hand, choosing how to attach to the measurement object itself. How is it mounted? Where is it placed? How is it used all together with the measurement device? That's all stuff the human itself, the human which is measuring the object, can influence, should influence, and should control especially. And for sure, things like the outside temperature, the humidity, and so on are all facts one can know and one should know and one should take into account for giving a measurement description, including the measurement value. So the main factor influencing our measurement is for sure the human. Now, additionally to things the human can know, there are some influences the human perhaps knows about. The person doing the measurement perhaps knows about some molecules jumping around and hitting randomly our measurement device. Yeah, that's thermodynamics. We know about it, but we have no possibility, no idea how to cope with that in respect to our measurement. We just don't know how to treat that stuff because we can't measure it exactly. In the end, there are quantum mechanical effects we know about, but we can't take into account for our measurement. So those are for sure unknown influences. But on the other side, for sure, known influences are the temperature or the humidity or the magnetic field of the Earth. Think about that. It's all around us and it's changing from place to place. We know that. We could measure it, but for most of our measurements, we won't think about things like the magnetic field of the Earth, indeed. So there are influences we for sure know about, meaning stuff like the outside temperature. That's something which is very important for almost any measurement, to know at which temperature this measurement was done. Because the temperature influences our measurement device, it influences our measurement object. And thinking about, for example, the resistance, it's for sure an influence which can't be ignored. Because the temperature heating up any material, nearly any material, will increase the resistance or decrease the resistance or change the resistance in any which way, but it influences the stuff. So that's something which one should take into account. Then on the other side, something like the magnetic field of the Earth, you are not able to take that into account most of the time. You know you would be able when you use some expensive measurement devices which give you a value for the magnetic field of the Earth, and in the end it will give you nothing. It will nearly give you nothing because it won't influence your measurement drastically. So that's a known influence we normally ignore. Nonetheless, doing two measurements at different places, those facts may be important for explaining why two measurements done exactly the same way, only at different places, may be different. That's something nobody would say it's not true, because for sure our guts tell us, man, when I'm doing a measurement over here and when I'm doing a measurement at the university, even if I have this exactly same setup, using the same measurement device, doing everything the same way, there are some circumstances which may produce different measurement values at that place or at another place or at any other place. Which are those influences? For example, the magnetic field. Perhaps there's some wind around that other measurement place we don't recognize. It may be small, but it's cooling down your measurement object, changing the measurement, and so on. So there are certain facts which we know about, but won't take into account for our measurement. There are other facts, like the temperature or the humidity, which we should take into account and most of the time take into account for our measurement. And there are some things, some error influences, like thermodynamics or like quantum mechanics, we can't take into account. So the latter, like thermodynamics or quantum mechanics, most of the time obey statistics. So we have some statistical methods to cope with them. We'll see what that means in chapter 3. The other stuff is something we as humans should treat as good as possible. Meaning nobody would expect that you are able to give every single context of your measurement exactly, that's nothing which can be done because there are so much influences. But one would expect to give the main influences, like, for example, the temperature, which is an important influence at all. Okay, talking about errors, I already said a measurement value without a measurement error is practically worth nothing. And even the best measurement devices have errors. A good example for that is there's a planetary orbiter launched in 2019 to the Mercury, measuring the surface of Mercury by doing a time of flight measurement with light. So light had a speed of 3 times 10 to the 8 meters per second, roughly. And the measurement device had a temporal resolution of about 1 to 2 nanoseconds. So that's in the gigahertz range. So it's exactly what nowadays one can easily provide within a rough environment like next to Mercury in an orbiter. So having said that, even with those best conditions, only using time of flight, meaning the speed of light, and the minimum time interval we have, we get an error of about 30 centimeters. That's nearly half a meter, and that's a big error, actually. Imagine you are going on the surface of Mercury, suddenly there is a wall half a meter high. Including all measurement influences, we have a measurement error of about plus minus 2 meters for that orbiter. And now imagine you are walking on the surface of Mercury and you're hitting a wall which is 2 meters high or even 3 meters high. That makes some difference. So the error is important even for very, very high-end measurements. Perhaps especially for them to give a rough idea why those measurements are high-end, because the error is the thing which defines the quality of your measurement. That's another fact one should know about. Okay, now let's define something about the error. The idea is quite easy. We have that measurement quantity we want to know. You already realized we never can know it because it's part of our measurement object, and our measurement value only gives us an idea of our measurement quantity. So in the end, the error, which I mark with a delta, most of the time is best described as the difference between the measurement and the real value, the actual value. Yeah, that's nice, that's obvious, but it's, again, useless somehow. We don't know that value. We simply don't know it. But the definition is fine. So, talking about that, perhaps we don't know about that, but perhaps we know something about that. Because we have our units, we have our standards for our units, which give us an idea of how the quality of our measurement device is, how big the errors may be. Maybe in a maximum way. So, taking your measurement device and comparing it to a unit standard, you will be able to give a maximum range of errors you have for your measurement device. Even if you're not sure about the minimum error you could use for your measurement device, you can give a maximum error, because you can always add some error space to be sure you don't tell something bad about your measurement device. So in this definition, the error itself may be given, may be possible to know, opposed to the actual value. But turning it around again, we see the actual value is something about our measurement value and the error. So just writing it down like that explains a lot. So now let's put in a plus minus here. For sure, that makes no difference. It's just about changing the sign. And we have that thing we normally write down when writing down a measurement value. The measurement value plus minus the measurement error. And now that explains why this definition makes sense at all. In parallel to this definition, we can have some definitions of how these errors are called. So what we've written down here is the absolute error. Awesome, well defined. We can turn it around and use it somehow. And in addition to that, often the relative error is used, which is defined as the absolute error relative to the actual value. Again, that definition is not perfect because, as you see, we have that actual value in there, but we can do a very good approximation at this point by just approximating that actual value in the denominator by the measured value. Why is that a good approximation? Because that's the reason why we're doing the measurement. So when the measured value wouldn't be a good approximation for the actual value, the measurement itself wouldn't be sensible. So that approximation is always okay. We can do that. Having said that, one may ask about why to have that relative error. In principle, there's no real reason for that, but the talking about errors and what humans can feel defining those errors. So comparing errors means, for the absolute error, comparing real error values. Meaning we have an error of 2 ampere or we have an error of 2 milliampere. Okay, sounds awesome right away. But now compare that to another measurement with an error of 2.5 ampere or 2.5 milliampere. So which measurement is the better one? Yeah, one would assume the measurement with the 2 ampere error is the better one, but perhaps it's part of a measurement which measures real high currents, like 5,000 or 6,000 amperes. And the other error is part of a measurement which measures real small currents. And now that brings in a little difference, because measuring a value of 5 ampere plus minus 2 ampere is something different than measuring a value 5,000 ampere plus minus 2.5 ampere. So the error in the latter case is larger, but the former case had such a small value, it's like half of the value is error, like 5 ampere plus minus 2 ampere. That sounds bad. That really sounds bad. And now our relative error gives us a glimpse for that. So in the case of 5,000 ampere plus minus 2.5 ampere, we get an error of sub 1%. That's low as a relative error. In the other case, 5 ampere plus minus 2 ampere, we get an error above 20%. That's a huge thing. That's the reason why we want to have the relative error. Now, having said that, that relative error has some problems. So imagine you have a measurement device which gives you the temperature of water in degrees Celsius. So over here we get the temperature, and now we see over here we get the temperature, at the x-axis, and here we want to denote the relative error. And now we see something. Imagine here's 0, here's 1 degree Celsius, and so on. And now we see that relative error, no matter how large the absolute error may be, will rise to infinity when hitting 0. That's a bad thing about the definition. Having small measurement values makes the relative error useless. So imagine some point near 0, like 0.1. And now that would be the range of the error itself most of the time for most temperature sensors. 0.1 degree Celsius, plus minus 0.1 degree Celsius. So we would have a relative error of 100%. That's useless. So when going more in the vicinity of the 0, we would even get larger errors, like 1,000% or something like that. That makes even less sense. Now one could say, okay, degree Celsius is bullshit, let's have degree Kelvin. Okay, we could use degree Kelvin and we would get an error, a percentage, which makes sense again. Because we would have something like 0.1 degree Kelvin divided by 273 degree Kelvin. Yeah. That would give us a value which has a usable percentage. That makes the relative error usable again. But in the next step you could use Fahrenheit and you would get a different relative error. So changing the units is not the proper solution for it, because in the end the units are the basis for all discussions. So talking about temperature, perhaps it's essential to talk about degrees Celsius for that certain measurement context or measurement environment. So you cannot simply change your units most of the time. So having said that, you should always be aware of the fact that those relative errors will rise drastically when having measurement values around 0. At that point, at that region, those relative errors make no sense anymore. Okay, in the next part we will talk about some error definitions, how to define errors and what most of the time we get from our data sheets of our measurement devices. And in the last part we'll talk about error propagation, another important topic. So when you enjoyed the stuff, don't hesitate, just subscribe. I will continue to have those simple, explainable, context-intensive, focusing lectures and chapters, and don't hesitate to ask questions, because I'm willing to do some extra videos explaining questions and so on.